So this lesson is going to be on functions of several variables. And the first one I want to look at is f of xy is the square root of x squared plus y squared. So what is this? I mean, can we plug in values? Sure, I can look at f of 1 comma 2. What would that be? That'd be the square root of 1 squared plus 2 squared, root 1 plus 4 is root 5. And so a point on that graph would be x is 1, y is 2, z is root 5. But what would the entire graph look like? We have any idea what that graph would look like? Well, fortunately, we have Desmos. Let's go ahead and jump there and see what Desmos tells us about it. Well, what do we have? We have this thing. We have f of xy is the square root of x squared plus y squared. It looks like a cone. That's interesting. So it's an elliptic cone. Look at our behavior there. Now, we want to talk about something else, namely level curves. So what are level curves? Level curves are of the form f of xy equals a constant. So, I mean, here could we have f of xy equals -2? No. -2 is not in the range of this function. You see that square root of x squared plus y squared is going to have to be something positive. So that's not going to work for us. But we could have f of xy equals 1. We could have f of xy equals 2. We could have f of xy equals 3. So let's jump to two-dimensional Desmos and look at all of those level curves. So if I have f of xy root x squared plus y squared equals 1, I get that circle. Equals 2, I get this circle. Equals 3, I get that circle. Now, can you imagine these things kind of being elevations? These are all the points where the height is 3. These are all the points where the height is 2. These are all the points where the height is 1. And we also have a level point, if you will, at 0. Can you sort of see the cone by looking at this two-dimensional representation? That's something that we'd like to be able to envision if we can. Now, I want to take a quick look at the three-dimensional thing again. So here is the cone we had before, f of xy, and here's f of xy equals 1. Notice there is that level curve, right? There is the intersection where the height is 1. Here would the intersection where the height is 2. And 3, etc. So all the points where the height is 3 gives me that level curve. So that's what that means. That's what a level curve is. But there's not just level curves. There are also not just functions of 2 variables. We can have level surfaces for functions of 3 variables. So let's say, for example, I'm looking at f of xyz equals x squared plus 3yz plus 2z cubed. Can you think about what that graph would look like? When you think about that, well, you can't because it would require 4 dimensions. But the best we can do is look at level surfaces. So level surfaces are of the form f of x, y, z equals c. So this time I do believe I could have a negative number that shows up. So let's take a look at x squared plus 3yz plus 2z cubed equals -1. Maybe let's look at that level curve. And again, you can do it for any constant you want. Maybe x squared plus 3yz plus 2z cubed equals 2. Maybe x squared plus 3yz plus 2z cubed equals 15. So let's look at those 3 level surfaces, actually, is a term I should use. Level surfaces for any constant c, just to get an idea maybe about how this surface is behaving. Okay, let's go ahead and take a look at those level surfaces. So here's a situation, x squared plus 3yz plus 2z cubed equals -1. Kind of interesting. All right. Want to zoom it out once? You get any kind of an idea? It looks essentially the same. Let's go to the second one where it equals 2. Want to zoom that out? Any change really? Not really. You get the basic idea of that shape. And how about equals 15? Oh, another kind of interesting thing. If I zoom that out, we get another feel for what that level surface represents. So kind of interesting. We cannot visualize the entire function. Again, f of x, y, z equals x squared plus 3yz plus 2z cubed would require 4 dimensions to be able to see the whole thing. Something to think about. Back in earlier algebra courses, we had to make sure that a function would pass a vertical line test. Remember, our first example here was a cone. That cone certainly passed a vertical line test, so that would be a function. But that level surface I just looked at, right? That level surface I just looked at would not be a function because that level surface would not pass the vertical line test, right? Vertical line would hit more than one thing. So a level surface doesn't need to be a function, but a function of several variables certainly must pass the vertical line test. Another thing we talk about with functions are domains and ranges. So the domain is a set of all possible inputs, and the range is a set of all possible outputs. So think about this for a second. What will the domain be? All the possible inputs. What will the range be? All the possible outputs. Well, we know for real valued functions, the thing under the square root has to be greater than or equal to 0. So y is less than or equal to x squared will be my domain. So if I want to write it in set form, I would say the set of points x, y such that y is less than or equal to x squared would be my domain. But sometimes we just like to draw a graph of this. Y equals x squared is a parabola opening this way, and when is y less than or equal to x squared, it looks like this. So we're going to look at our graph, and hopefully that will be supported. Now, how about the range? The thing under the square root, the lowest it could ever be is 0. Plus 4, so the lowest this gets to be is 4. So the z values, again, f of xy corresponds to z. The lowest possible z value is 4. How high could it be? Well, if y is 0, for example, x could be a million or a billion or a trillion. This could get as big as you want. So the range is going to be from 4 to infinity. So can we see that when we look at the graph? So I have it here. I put a green dot at the point 0, 0, 4, so you could see that indeed this height is at z equals 4, and you see it never gets below that. Now, how about, and it goes as high as you want, or so it appears. Now, how about the domain? Can we see that it's y less equal to x squared? Not so much with this view, but once I look at it from on top, aha, you can see the y equals x squared parabola. And you can see all of the blue dots are under that. So from the top view, you can see the only points x, y that we're using are the ones under that parabola. Okay, here we're going to look at g of xy equals 2 plus square root of 9 minus x squared minus y squared. And think for a minute, can you identify what the domain and range are going to be? Can you think about what the graph is going to be? Well, similar to the last problem for the domain, the thing under the square root's got to be greater than or equal to 0. So 9 is greater than or equal to x squared plus y squared, which gives me x squared plus y squared less than or equal to 9. Do we recognize that from geometry? What is that going to be? Circular radius 3. Everything centered at the origin. Shade that in, and that's going to be my domain. So we want to see how that is going to be reflected in the graph. The range corresponds to the outputs. Now, how low can this get? Again, the lowest the square root could ever be is 0. So the lowest the whole thing is going to get is 2. But now, how high does it get? You might think this can get as big as you want, but no. If x is any kind of a number, x squared is positive. Similar with y, y squared is positive. So these will always decrease 9. 9 minus something minus something. So the highest this will ever be is root 9. or 3. So what I have is I have a situation. I have 2 plus, the lowest it ever gets is 0. The highest it ever gets is 3. So my range would be from 2 to 5. Now, what do you expect that to look like? Any idea? The entire graph is over this little circle. It gets as low as 2, it gets as high as 5. So let's take a look at the graph. Here we go. It's a little cap. We believe the range goes from 2 to 5. Let's take a look. Ooh, that's going to get us dizzy. So let's go ahead and draw in the plane z equals 2. Is that as low as it gets? It never gets any lower than that. All right, so that looks pretty good. And we think it goes up to z equals 5. Is that right? Is that as high as it gets? Z equals 5. That looks like that's good too. So indeed, our domain then is what? What is our domain? If we look at this from top, boom, is that circle from 0 to 3? Well, for example, let me go ahead and put in the point 3, 0, 0. And you can see that it's that point on the circle as it's spinning around again. So our domain and range will look pretty good here. Our domain is everything in that circle and its interior, and our range is from 2 to 5.